So in this video we will study about the some application of the Lewis dot structure and how to use the Lewis dot structure and what the information it can provide. So Lewis dot structure can provide relative bond is length. So which bond is short, which bond is length, I mean the shortest distance between the two bonds, that bond length can be provide bond length information can be get from the Lewis dot structure. Number 2 is between predict the bond strength, also how strong these bonds are. And number 3, it provide or predict the three-dimensional geometry, so how they are arranged. For example, in methane, how these 4 bonds are like this one, or these bonds are like this HHH, or they are like this one, or they are really 90 degree, or they are like this. So what is the three-dimensional geometry? So predict, and they are also predict the boiling points and vapor pressure, and predict the relative solubilities also. So these are the some applications of the Lewis dot structure which can be very beneficial. So let's see one example first about the bond strength and bond length. So bond strength, triple bonds are stronger than the double bonds, which are stronger than the single bonds. So triple bonds are the stronger bond, they are stronger, and then the double bond come, and then single bond come. So if we need to break the bond, single bond, this is single bond, this is double bond, this is triple bond. So if we need to break the single bond, it's very easy. Breaking the double bond is comparatively harder, and breaking the triple bond is really harder. So the strength of the bond is like triple bond is the strongest bond, double bond is less strong, and single bond is very weak. So this is the bond strength can be drawn like this one. And another example of the application is the bond length. So triple bonds are shorter than the double bonds, which are shorter than the single bond. So triple bond are shorter. So I will say these are the shortest one. This is short, and this is shorter. This is short, and this is short. So this triple bond is really very small. So the distance between the two atoms is very small compared to like this one, and the single bond like this one, right? So let's see one example so we can understand this better. So here is example of carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. This is called ethane, this is ethene, this is ethyne. And bond strength, as we have seen, that single bond is less strong compared to double bond. And double bond is more strong, and triple bond is the strongest one, so it need more energy to break it. But they are not as 3 times of much, right? And here is double bond. So yeah, it's not as a 3 times, it's not as a exactly double. And double bond, so bond length Single bond is the longest one. You can see the distance between the two single atom is largest, and then this is short and this is the shortest one. So triple bond the shortest and strongest. Double bond is strong and short compared to single bond, and single bond is the weakest and longest. So single bond can easily be break compared to the double bond, compared to the triple bond. So this was about the bond length and the bond strength, and we will see about the enthalpy of the reactions. So bond strength can be used to predict enthalpies of reaction also. So as we have seen that a single bond are the weakest one, it can easily be broken, and this reaction shows that carbon bromide CHBr3 when react with the chlorine gas, it forms ClBr3 and HCl. So what happened here in this bond formation, and so this chlorine bond broke, carbon hydrogen bond broke, so there are two bonds are broken, and you can see there are two new bonds are forming. Carbon and chlorine bond is forming, and hydrogen and chlorine bond is forming. So two bonds are broken and two bonds are formed. So we can also predict what is the enthalpy of the reaction, means how much energy is releasing out or how much energy we have to give it. So how we can do that? Using bond enthalpies, there is a table which in the next slide. Table 8.4 estimate delta H for the following gaseous phase reaction. So this reaction will be occurring in the gaseous phase, and where there two bonds are broken and two new bonds are forming. So let's see how this enthalpy will work. So this is the table for the bond formation and bond. So this is the table, basically average bond enthalpies. So each single bond have how much energy in it, when we will broke, how much energy will come out, or how much energy is required. So when we will calculate based on this table, so you can see that the bond enthalpy, so two bonds are being broken. So we are talking about this reactant side first. Chlorine bond is broken, and carbon and hydrogen bond is broken. So carbon and hydrogen bond is broken, means it is endothermic reaction, and so delta H will be positive. So it means we have to give energy, means they have 413 kilocalorie per mole and then 242 kilocalorie mole per mole, and the two bonds are being formed. So chlorine bond is chlorine and carbon is bond is forming, and hydrogen and chlorine bond is forming there. So two bonds are forming and two bonds are broken. So two bonds are forming means it is an exothermic reaction, energy is coming out. So what will be the difference between the whole reaction? How the energy flow will work? So what we will do, we will calculate that delta H will be equal to bond broken plus bond formed. So bond broken, these are the bond broken energy which are endothermic, and the exothermic reaction will be in the minus. So bond formed, we have to put these values in the minus and these values in the plus. So bond broken will be in the positive form and bond form will be in the negative one, and when we will calculate, it will come like minus 104 kilocalorie. So look like this is an exothermic reaction. When the these two reactants react together, they releases some energy out. So this is the way we can calculate the strength and enthalpies of the bonds using Lewis dot structure. And the last slide of this video is bond comparison. So when you will make a chart like a series writing the covalent and ionic bond. So covalent bonds, so all single bonds are equivalent? No, single bonds are not equivalent. Hydrogen and hydrogen, they are also single bond. Hydrogen and chlorine is also single bond, and cesium fluoride is also single bond. But cesium fluoride is a minus and plus. This is an ionic. It is too much polar compared to chlorine HCl. So this is plus, this is minus, and these are the same. So all single bonds are not the same. That is why they have some polarity if they are with the similar type of atoms with the equal sharing of electron. They are forming non-polar covalent bond. But if the electron density is unshared, if electron density is not evenly shared between the two atoms, there will become polarity will increase, and at the end the highest polar they are will be ionic bonds. So this was all about the chapter number 8, the bonding and Lewis structure, their exception we have gone through. So please keep review these videos and let me know if you have any question, and I will try to answer you.